All right, so in the last two steps, just so you can see where we're going, now we've moved the phosphoester. We've moved the phosphoester from, and I'm going to highlight the phosphorus and the oxygen. And I'm also going to highlight what it's attached to give you an indication that, or just a preview, that ultimately we want this phosphorus to become the gamma phosphate of ATP. We want to do another kinase style regenerate ATP by having that phosphate attached to a good leaving group. The problem here is it's currently a phosphoester, and the leaving group would be OR minus, which is tolerable but not great. And you can see this if we tried to take ADP right now plus the phosphoester and go to ATP and an alcohol, that would be going from level 2 to level 1. That would be uphill. So we're not yet set up for that, and the remaining steps of glycolysis are all about getting us to the point where the thing the phosphate is attached to is a better leaving group. So if you look at what we do in this mutase step that we didn't talk about very much, the phosphate group is now on the C2 hydroxyl. It's still a phosphoester. It's still attached to something that is not a great leaving group. So it would still be uphill to go from a phosphoester to ATP by having ADP attack this blue phosphorus to make the ATP where that would be the gamma phosphorus. So we need a little bit of help to make what's on the green side of things an even better leaving group. And it turns out we only need one small, simple step for that to happen. So let me show you that step, and that's in your quiz. We start in your quiz with 2-phosphoglycerate, and afterwards we have phosphoenol pyruvate. And you have to sort of pay attention to see what's going on here. There's a hydrogen in the starting material that's not in the product. There's an OH group in the starting material that's not in the product. And there's electrons from the hydrogen-carbon bond that look like they end up as a lone pair. And that seems to be supported by the fact that the OH group and the hydrogen end up here as water. In fact, I could redraw the water like this and maybe make the point even more clearly. We lose a hydrogen and we lose OH minus. This reaction, is because we lose water, is called a dehydration reaction because we're removing water. Now the intermediate here is shown. The intermediate actually has a negative charge on an atom that is alpha to a carbonyl. And you've seen that this is possible because the negative charge that's alpha to the carbonyl can actually donate and be stabilized by resonance with the carbonyl group. So this reaction has an enolate as an intermediate, and then after the enolate forms, we get the pi bond forming an OH leaving. So let's talk about what the right arrows would be. To get from the starting 2-phosphoglycerate to this intermediate, what does it look like I have to do? Deprotonate. That's so from the base to the hydrogen. Now, what do I do with the pink electrons that are the ones in the carbon-hydrogen bond? Where do those go? They can go onto the alpha carbon. There's another option The other option is simply the resonance structure of the enolate. I could have drawn as a resonance structure of the enolate the following. Just going to abbreviate the phosphate group like that, and then the rest of the molecule like that. To get to this resonance structure, I would, and I'm going to use the resonance double arrows to indicate that those are two resonance structures of the same thing. To get to that resonance structure, I could have pushed these electrons here to form a pi bond and then broken the carbon-oxygen pi bond. Those are two equally legitimate options for the mechanism of this reaction. To me, it's clearer just to put it on the alpha carbon. All right? So that's the enolate. Then, comparing the enolate to the product, what do you think has to happen? Okay, the alcohol's got to be lost. How do you think that occurs? Yeah, we've got a kicker offer there, right? A lone pair adjacent to a leaving group. An OH minus is not that great as a leaving group. Fortunately, we have the conjugate acid of our base there that can help things along. So electrons kick down to make the pi bond. Leaving group leaves. And as it's leaving, it pulls the proton off the conjugate acid of our base. All right? That's the dehydration reaction. You're going to see that type of reaction. Are you going to see that reaction? Yes, probably in a future metabolic reaction. Go ahead.
Do you have to break like the pi bond between the carbon and the oxygen because it's the LUMO or not?
Do you have to break the pi bond between the carbon and the oxygen because it's the LUMO? Great question. Notice that the nucleophile is not attacking the carbonyl carbon, so you don't have to break the pi bond. Now, the question that I think you're asking is, if the LUMO is the carbon, is the pi star, then how is it that the nucleophile ever attacks the proton? I can show you an answer. It will likely blow your mind, and it's okay if it doesn't understand, but I can't resist since you asked. Is that okay? Yeah. All right. So I'm just going to draw a simple carbonyl compound that has a methyl group adjacent, two methyl groups adjacent to the carbonyl carbon. This is acetone. You can see the carbonyl oxygen. There's no laser pointer on this. That's the carbonyl carbon, but I can't reach the carbonyl oxygen. That's so cool. I love that. Now I'm going to show you the orbitals. The pi, well, I'll show you the LUMO, okay? Now, part of the LUMO should look familiar. This part of the LUMO, it looks like a pi star. There's a node in between the carbon and the oxygen. Opposite colors indicate switch in wave function sign. This is the carbonyl carbon, that's the carbonyl oxygen. But some of the LUMO has spread out onto these protons that are adjacent to the carbonyl carbon. Those are alpha protons. There is a great explanation for why that happens. It's just beyond the scope of the class. If you want to know more, we can talk about it. It's something called hyperconjugation. But that's the answer, is that a nucleophile that looks at a carbonyl can choose to attack the LUMO at C or at the alpha proton. If it attacks at the alpha proton, you get an enolate. If it attacks at the carbonyl carbon, you get an addition product. Yeah. Okay, good. Other questions? Yeah.
Will you ever give us like the start and then say which is more likely to happen? Like, will it attack this or will it attack this?
So which is more likely to happen? Will it attack this or this? If I were going to do that, you'd need to have knowledge of where the reaction is supposed to end up. So yeah, I mean, that's a decent question for this a mechanism question for this reaction. If I show you the starting materials and the products, and then I show you a mechanistic step where you're attacking the carbonyl carbon, yeah, you'd need to know, well, that doesn't make sense because nothing adds to the carbonyl carbon. Yeah. Others? Okay. Last step of glycolysis is to take what we just made, the dehydration product, phosphoenol pyruvate, and now we're ready to make ATP. And it's not going to be immediately obvious to you why this is the case. Remember that our big problem up here and before is that the phosphoryl group that we want to attach to ADP isn't attached to a great leaving group. So we needed something that's a better leaving group. Our solution was, well, let's just do a dehydration reaction. So now we have phosphoenol pyruvate. So the question is, what about that? Is that a great leaving group or what? So let's look at, again, think about the phosphorus as the electrophile attacking the phosphorus oxygen pi star. The nucleophile is going to attack the phosphorus oxygen pi star. This is going to become the gamma phosphorus of ATP. And we're going to say all of this is a phosphoester. All of that's a leaving group. The functional group here is a phosphoester, but it's more of a phosphoenol ester, meaning the alcohol that is attached to the phosphorus is not a typical alcohol, it's an enol. And that's important because let's imagine what would happen if that leaving group left. Sometimes, as you know, we protonate leaving groups to help them leave. Where would you imagine protonating this leaving group? I will give you a hint. There are two spots. One of them is obvious. What's the obvious one? Yeah, if you protonate on the negatively charged oxygen, you're going to get this enol. If you protonate, where's the other spot you could protonate? Yeah, this carbon here, right? If we protonate on that alpha carbon, what I've shown you are the resonance arrows that should convince you that that alpha carbon shares the negative charge from the oxygen. If we protonate on that carbon, then the product is a ketone. And one of the things we learned, or that maybe you remember, is the keto form. The keto and the enol forms are tautomers. They differ only in the location of a pi bond and a proton. And the keto form is more stable than the enol form. So this phosphoenol ester is spring-loaded to become an even better leaving group than it is after it leaves. All right. So let's show you how that reaction happens. Or are there questions about what I just said? Yeah, go ahead.
So the keto is the one that has the methyl group?
The keto form is the one that has the carbon oxygen pi bond. And has the CH bond. I mean, there's several, but it has an additional CH bond on the alpha carbon. The enol form has a carbon-carbon pi bond and an OH sigma bond. So those are the differences. And it turns out that carbon-oxygen pi bonds are more stable than carbon-carbon pi bonds. All right. Other questions? Yeah.
And that then works because a ketone is a level 1, so like when you get the ATP, it's not changing.
Right, so the question is that, it would be nice if it worked out that way. Unfortunately, the ketone is a product too, so you're generating two level 1 compounds. That gives you a sense though for how unstable phosphoenol pyruvate must be relative to these. So yeah, if the ketone is a level 1, the enol must be even higher because it's less stable than the ketone. The other thing that makes phosphoenol pyruvate unstable is how close the carboxylate is to the negative charge on the phosphate. So there's some charge repulsion that gets relieved when you make ATP. Okay, so let's show you just the mechanism of that pretty quickly. Most people will draw this, well, what do I know? So it may make, I'm not sure how to explain this in a way that'll be useful. Let's look at the lone pairs on the oxygen that's in our enol functional group. And let's just draw the resonance structure that shows that the carbon that is adjacent to the oxygen, which I'm going to call the alpha carbon because it's one carbon away from the oxygen. Let's just show that one with a negative formal charge on it. The oxygen from the phosphorus should have a positive formal charge on it. And then we'll draw the rest of the phosphate group and the rest of the carboxylate. Now, I understand that that looks ick to a lot of you because of all the charges. What I'm trying to communicate is that the lone pairs on this oxygen are delocalized out onto the alpha carbon as well. And that the alpha carbon, the blue alpha carbon, the one that's adjacent to the enol, is electron rich. Okay? So what we're going to do now is a proton transfer reaction. And that proton transfer reaction, the net effect of it is going to be to make the enol leaving group even better. So we'll have the negatively charged alpha carbon attack the hydrogen of the acid. That's going to generate an intermediate that looks like this. Two of those three protons are always there. I guess maybe it's confusing for me to draw them all, whatever. Now, the effect of that proton transfer is to turn what's here, and I'm sorry, I know I need a positive formal charge on that carbonyl oxygen. This is now a great leaving group because it can leave as the neutral ketone. So now this thing is primed to be attacked by a nucleophile, and the nucleophile is ADP. So again, we're just going to draw maybe just the beta phosphorus of ADP. We'll show lone pairs on that beta phosphorus attacking what is going to become the gamma phosphorus. Electrons move out onto the oxygen. We'll redraw the intermediate. In which the phosphorus is attached to 5 different things. Here's the new bond with the beta phosphoryl group of ADP. Here's the negatively charged oxygen that's going to act as a kicker-offer. Here's the ADP nucleophile attached to the gamma phosphoryl group. And then here's the leaving group. And electrons on the negatively charged oxygen kick down and leaving group leaves. You generate ATP and the final product of glycolysis, which is called pyruvate. And it turns out, even though you're making ATP and this ketone, this reaction, this leaving group is so good that this reaction is very downhill in energy and is irreversible. This is the one, there are 3 in glycolysis. The first 2 were easy to predict. Phosphoanhydride to phosphoester, no problem. The last one is hard to predict. We started out with phosphoenol pyruvate, which looks like a phosphoester, but because it's a phosphoenol ester, it has the potential to become a super leaving group just by a simple proton transfer reaction. And that's what happens, and that allows us to generate ATP. Yes?
You're saying it's higher than level 1?
If a ketone is level 1, an enol is less stable than a ketone, so it should be even higher. I would say this is, it must be higher. I don't know what we're going to call that, level 0.5, but it is, yeah, it's like level 0. That sounds ominous. But it's, yeah, it's higher in energy than level 1 in the sense that it's downhill to get both the ketone and the ATP products. Okay.
So it has the potential to be higher if it has the right enzyme?
Well, phosphoenol pyruvate, once it gets protonated, once this part gets protonated, then it becomes an excellent leaving group. Yep. All right. So that's glycolysis. Now, if you looked at that, you might say, I think there's more to be done here, because you still have a ketone. That's a level 1 reactive molecule. It might be reasonable to generate some more molecules of ATP from that. There are in fact, your body does extract more energy from pyruvate. There are some organisms, however, that only do glycolysis, and there's evidence that a long time ago, organisms that figured out how to do the electron transport chain got co-opted and became our mitochondria. So your mitochondria, which do oxidize pyruvate in the citric acid cycle and do the electron transport chain, they have their own DNA. It's almost as though they were an organism that was captured in the way distant past, which is kind of cool and kind of like evil galactic empire, Sith Lord kind of action, right? The mitochondria are forever stuck in the spice mines of Kessel. Does anybody get that reference? No, it's okay, don't feel bad. Nerd alert. Okay, so what we want to do now is talk about what happens to pyruvate in eukaryotes. These are organisms that have mitochondria. And I'll take you back to the lecture notes. There we go. Pyruvate ends glycolysis, and the last 2 molecules of ATP that are generated, those are now free and clear profit. Okay, that's our profit, 2 ATPs from glycolysis. Let's see, just an aside that doesn't matter too much. If you're an organism that only does glycolysis and doesn't have the electron transport chain, in order to do more glycolysis, you have to find a way to recycle NADH and turn it back into NAD+ so that you can do more oxidation chemistry. And what ends up happening to pyruvate is NAD+ ends up donating a hydride to this carbon to turn pyruvate into this molecule, which is called lactate. So you've heard of lactic acid before. It's associated, the concentration of lactic acid increases in your muscles when you're working really hard and your electron transport chain can't keep up with accepting hydrides from NADH, and therefore to recover more NAD+, your body reduces pyruvate to lactic acid, and that's sort of associated with some of the feelings of like, when you're old like me. Was it last Wednesday? No, it must have been 2 Wednesdays ago. I went with the teacher's quorum. I have a lot of callings. I went with the teacher's quorum to hike the Y on a Wednesday night, and I was the last one up the mountain. And by 10 minutes or more, I was like, yeah, well, thank you for indulging me. If I were in better shape, it wouldn't have been as hard. The funny part was that my 14-year-old or 13-year-old had been complaining. Like, he's in the teacher's quorum, and I'm a teacher's quorum advisor, and he's like, Dad, I don't want to go. I don't want to hike the Y. And I'm like, but you have to go. Why do I have to go? I shouldn't have to go. Well, I'm kind of the advisor, and if I go and don't let you go, what does that say about? And there was a whole thing, and I finally stopped trying to reason with him and resorted to threats. And the threat was big enough that he decided to go, but he yelled at me about it. And now all of this is going to be on YouTube forever. I'm sorry. Maybe I'll go back and edit this part out. I don't know. But anyway, then he went, and because he was with his friends, he had a great time. I mean, he hiked up fast, and they all took their shirts off because 13-year-old boys are anxious to do that to whatever. And so anyway, he had a great time, and afterwards he was like, Dad, I'm sorry, it wasn't as bad as you thought. So your spiritual thought today is, how many times are we, like my 14-year-old son, griping, belly aching about some hard thing that we're having to go through, and then we actually go through it, and it was actually for our good, and it turned out okay, even though it was really hard. There's a ton of things in my life right now that feel like really hard things that I'm belly aching about. I know I am one of those things in your lives right now that you are belly aching to people about. Just stay on the path and trust that the Lord's strength will help you get there. You may need to take your inhaler if you're like me, though. Total classic nerd, right? Star Wars, asthma, inhalers, out of shape, checking all the boxes. One other thing that's neither here nor there, periodically on Saturdays, you can do this in spring, actually. You can't do this so much in a fall semester. My wife took a class here in a spring term, and she said the professor did nothing but talk about where good places to go for hamburgers were. Unfortunately for you, this is not that class, but I will tell you one other story. We have Costco Saturdays, which I think we always see people in your age eating at the Costco food court, so we think this is a thing. Like, it's 20, even on the island of Maui, where they have to import the hot dogs, they're still $1.50 on Maui. It's just a great American tradition. But in any case, we drive to Costco, we pass this park by the Sierra, and there's always medieval LARPers there on Saturdays. So if that's your crew, that's where they go on Saturdays, and broadswords and stuff, and we always sort of look and say, oh, look, there are the LARPers. But Amber said to me once, she hates Costco, she doesn't go, but on the subject of LARPing, she said, Josh, you're totally a LARPer. And I said, no, I'm not. She said, do you own a costume from a sci-fi/fantasy franchise? Yes. Have you worn that costume in public? Yes. Have you worn it not on Halloween? Yes. Do you have a weapon associated with that franchise? Yes. Have you ever worn your costume in public and brandished the weapon at other people while not on Halloween? Yes. Your Honor and jury, I submit the only verdict you can render is guilty. And at that point, I pled guilty. Yes, I guess I qualify. But I think lightsabers are way cooler than broadswords. So the burger place, yeah, I don't know. This was a guy in the old social work department. I don't know what I don't know what the best burger place is. So sorry, I'll go ask, maybe next time. Okay, so we need, this part is hard. We've saved it for last, and that's why I gave you a break and told you an amusing anecdote, and a semi-amusing anecdote from my life, because this one's difficult. End glycolysis with pyruvate, but pyruvate still has 3 carbons, and those are all going to get oxidized to CO2 in your mitochondria. And the first step in all of that is conversion of pyruvate to acetyl-CoA. So I need you to pay attention to what's happening here and where things go. First, carboxylate, which you've learned is level 4 in reactivity. Here's the carbonyl carbon. Here's a negatively charged oxygen. Both of those end up here in CO2. Maybe I'll make the other oxygen gray just so that we have something. All right, so that carboxylate group ends up as CO2. And these 3 these other atoms, the 2 carbons and the oxygen, end up here in acetyl-CoA. Coenzyme A thiol is the nucleophile. It loses a proton. The electrons in this bond between the carbonyl carbon and the thiol come from the bond between hydrogen and sulfur. I should have drawn it out. I didn't here. I'll just draw it like that. So in effect, if you look at the electrons in this bond between the green carbon and the blue carbon, they're not there in the product. They have to go somewhere. The electrons for the pi bond in CO2 come from this lone pair on the pink oxygen. So the electrons in this bond between the blue and the green carbons have to go somewhere. They're removed from the molecule, which means this is an oxidation reaction. And so it's no surprise that we're using NAD+ to do this. But we're not really set up, and it's not a simple process because there's no hydride to be removed at this stage. When we've done an NAD+ based oxidation before, there was an intermediate where there was a lovely hydride to be eliminated and accepted by NAD+. So we've got cofactors to help us out. One of them is this molecule that you've never seen before called thiamine pyrophosphate. The important part of thiamine pyrophosphate is all here. And right now, you can think of thiamine pyrophosphate as being a nucleophile at the negatively charged carbon. There's a lone pair on that carbon that's nucleophilic. The second cofactor is called lipoamide. This is actually a permanent prosthetic group on a protein side chain. So this is a lysine side chain that's tied up in an amide bond with what's called lipoic acid. And this sulfur here ends up being electron poor. Sulfur bonds are relatively weak. This is called a disulfide bond. Those show up in proteins, and we'll have more to say about them later. But disulfide bonds are relatively weak. And so that means that the LUMO of lipoic acid is the weak sulfur sigma star. And so a nucleophile can attack at that sulfur, and that's going to be important later on. One other thing I wanted to mention at this stage is that you have seen a reaction that generates CO2 before. You saw it in our mechanism handout. It was called decarboxylation. And the general pattern of decarboxylation that I told you, losing CO2, was when you have a carboxylate and the beta carbon has a keto group on it. So we've done decarboxylation of beta keto carboxylates. And the reason it works, as you recall, is we're going to use the negatively charged oxygen from the carboxylate as a kicker offer. This is going to become the CO2 oxygen. All of this is a leaving group. And the reason it works is because the electrons in this bond between carbon and the alpha carbon are going to end up on the alpha carbon where they are stabilized by resonance. The leaving group for decarboxylation of a beta keto acid is a resonance stabilized enolate. And you could draw, if you wanted to, the other resonance structure that would look like this with the negative charge on the oxygen. And then in a subsequent step, that enolate gets protonated on the alpha carbon, and that leads to a ketone. So you've seen that before. That's decarboxylation of a beta keto acid. The products are a ketone and CO2. And that happens spontaneously, no oxidation necessary. The electrons in this carbon to alpha carbon bond actually end up here as a lone pair on the alpha carbon, and then here as in the CH bond. So that's not an oxidation reaction. There's no loss of electrons. In contrast, notice the structural difference between a beta keto carboxylate and pyruvate. For pyruvate, it's an alpha keto carboxylate. And notice if we tried to do the same thing with pyruvate, we would need to put a lone pair on the carbonyl carbon, and that's a functional group that we've never seen before. And in fact, that's the conjugate base of an aldehyde, and you'd have to ask, what is the pKa of an aldehyde? And it's astronomical. It's like in the 40s. So terrible leaving group. So alpha keto acids like pyruvate, because there's no resonance stabilization of the leaving group, they don't do spontaneous decarboxylation. I know that penmanship is terrible. Instead, they can do decarboxylation, but they need a whole complex of enzymes, and they need 3 cofactors, NAD+, thiamine pyrophosphate, and lipoamide. And you'll see that it's the mechanism we're going to draw is supremely more complicated than this simple mechanism here. Okay? Alpha keto acids undergo what I'm going to call oxidative decarboxylation. Why is it oxidative? Because we have to have somewhere to put these electrons. This is important to get now because this kind of thing shows up one more time in the citric acid cycle. All right. So that's the overview. Now, details. So this is the last question on your quiz. I apologize that today I'm not turning you loose on many of these questions. I normally like to do active learning things where you get a chance to work on something by yourself and work your way through it. I'll probably give you that kind of chance on a problem like this in the future, but it's hard enough that I feel like it's worth it going through together. I encourage you though to take notes and follow along as best you can. So this summarizes what I just told you. Pyruvate, an alpha keto acid, it's going to go to acetyl-CoA. You're going to lose the carboxylate carbon and 2 oxygens as CO2. These 2 carbons of pyruvate will end up as acetyl-CoA. In the process, NAD plus is our oxidizing agent, and it gets reduced to NADH. That's another energy-rich molecule that we can exchange for ATP in the electron transport chain. I suppose the other cofactor we need is coenzyme A, which provides a thiol. Coenzyme A is a much bigger molecule than just the thiol, but we're going to just consider it to be the thiol for now. Everything else is just a handle for the enzyme to hold on to. All right. And as I said, thiamine pyrophosphate is a key cofactor. It's going to be our nucleophile. And we should draw a lone pair on the carbon in between the nitrogen and the sulfur. You can tell that that lone pair is there because the carbon has a negative formal charge, which means the carbon must own 5 electrons, whereas it normally comes with 4, and 4 minus 5 is -1. The nitrogen on the adjacent atom is positively charged, and that's important too. Okay. So, looking at the first step, I told you that thiamine pyrophosphate was going to be your nucleophile. This is something that I think you can predict easily. In pyruvate, you have a ketone and a carboxylate. Which carbon, the ketone carbon or the carboxylate carbon, is more electrophilic? Ketone. Ketone's level 1, carboxylate's level 4, not an electrophile. So, it should be no surprise then that we want the thiamine pyrophosphate, or TPP, nucleophile to attack the carbonyl carbon, which is what we've got here, and that's the new bond that we made. Here's what used to be the carbonyl carbon, here's what used to be the carbonyl oxygen. So you tell me how to push arrows to make that happen. Where do I start? Lone pairs, and then what? Attack the carbonyl carbon, that's the pi star, and then I do what? Break the pi bond. I could do there and draw an intermediate, or I could just protonate. And a lot of what enzymes do to accelerate reactions is they prevent the negative charge from ever forming on the carbonyl oxygen in the tetrahedral intermediate by protonating it. All right, there we go. There's our intermediate. Now, so you with me there? What kind of step was that? This arrow represents addition, and this one, these up here represent deprotonation. Good. All right. Now, if we look over here, it looks like we've lost CO2. And what we're left with is this molecule. And you'll notice that I've drawn some resonance arrows suggesting that this molecule is indeed resonance stabilized, not so very much different from an enolate. What I'm going to do at this stage is I'm going to redraw our intermediate so that I can label it with color a little differently than I did above. So here is the 5-membered ring of TPP. Here's the bond to the carbon. And here is the carboxylate group. Now we're going to consider all of this to be a leaving group. We'll call this oxygen the kicker offer, and this sort of the carbonyl carbon. And if this is the carbonyl carbon, this is the alpha carbon. What do you notice about the beta carbon? What is it? Oh, and I'm missing, you're right, I'm missing a positive formal charge on the nitrogen. Compared to what I told you before about beta keto acids, what similarities do you see between a beta keto acid that I just drew and this intermediate? What do they have in common? Their beta carbon is involved in a pi bond. Now that's not a ketone, But if you squint your eyes a little bit and relax and think, well, nitrogen's electronegative, kind of like oxygen. That's kind of that's a pi bond in the same way that this is a pi bond. You've got something there that's kind of like a ketone. And importantly, if you imagine this happening, electrons on the oxygen kicking down to form a pi bond, breaking the bond between carbonyl carbon and alpha carbon with electrons going on to the alpha carbon, that's what you get here. And importantly, that lone pair that came from the bond we just broke is adjacent to a pi bond. So that's a classic situation where resonance can happen. The negative charge on that alpha carbon is stabilized by resonance. I can draw arrows this way, form a pi bond here, break this pi bond, move it to a lone pair on the nitrogen to get this neutral, uncharged resonance structure. So the interesting thing is, remember I told you that if you tried to decarboxylate an alpha, oh, somebody was going to tell me to shut up, weren't they? Sorry, I got to finish the sentence. I gave you Darth Vader today, so you can handle it. If I tried to decarboxylate an alpha keto acid without ATP, as I said, I would get a non-resonance stabilized, negatively charged leaving group. The presence of TPP prevents that from happening. All right, fair enough. We'll pick that up next time. Have a good Thursday afternoon. I will see you tomorrow.